Welcome to this lecture on transition metal organometallic chemistry from principles to applications. In the last lecture, we have been discussing a very important topic on transition metal carbene complexes. In this particular topic, we have looked into various synthetic protocols that are available for making these transition metal carbene complexes. We have also spoken about the importance of transition metal carbene complexes, particularly with regard to their catalytic applications. We have also looked into various kinds of transition metal carbene complexes that are known, or the classification of transition metal carbene complexes, and these mainly are of two types, Fischer carbene as well as Schrock carbene, and their reactivity and properties as well as the methods available for preparing them are also different. With that overview, what we are going to discuss today is some more synthetic protocols that are used for preparing these transition metal carbene complexes, particularly the Fischer and the Schrock types. Now, with regard to transition metal carbene complexes, we had come across the free carbenes, which are called N-heterocyclic carbenes, or referred to as NHCs. Now, usually carbenes are extremely reactive molecule and very difficult to isolate and characterize, and from that perspective these NHCs are important because they are isolable and bottleable. Carbenes, and these are first prepared by Ardengo, which contain an imidazole on an imidazole based ring that contain imidazole with substituents on the nitrogen atom and a free carbene lone pair. Now, what it turns out that these carbene complexes, these carbenes when complex to metal shows remarkable catalytic property, and that is why NHC transition metal bonded NHC complexes have gained catalytic prominence. And in the last lecture, we have discussed that how these transition metal NHC complexes are formed, and one approach had been the reaction of free carbene with transition metal, and for example, treatment of this free carbene with M would give type of transition metal carbene complexes. We have also seen that transition metal carbene complexes can be obtained from the imidazolium precursors, which gives free carbene upon reaction with a base to give the transition metal carbene complexes. Now, of the types of imidazolium precursor, usually one of the type is the CCl3H bonds as shown over here, and it has a hydrogen and a CCl3 moiety, and these are called NHC precursor, which upon heating gives of chloroform CHCl3, leading to free carbenes that dimerizes to give an olefin, of the type shown over here, but this olefin does not dissociate to free carbene, whereas free carbene dimerize to olefins. So, carbene transition metal carbene complexes can be synthesized from the carbene precursor as well as carbene by treating it with metal precursor in presence of a base. Another very interesting method for preparing carbene from its imidazoline precursor is shown over here. For example, when this imidazolium salt is treated with or heated with mercuric acetate, that releases 2 acetic acid molecule, the proton of this CH bond that gets abstracted by the acetate anion, giving rise to NHC carbene complex of the type shown over here. And the same abstraction instead of the acetate can also be achieved by a metallate, for example, HCrCO5 minus, which when heated eliminates dihydrogen, the hydride, and this proton gives dihydrogen, giving this N-heterocyclic carbene chromium complex. Now, the beauty about this experiment is that this is NHC proton abstraction by an acetate moiety, and on this side the same NHC proton abstraction by an hydride of a metallate anion, and both yielding transition metal NHC complexes from this precursor, and in both case this acidic proton of the NHC precursor is abstracted. In this case it is by the anionic acetate moiety, and in this case the hydride of this metallate abstracts this proton, leading to evolution of dihydrogen and along with the formation of the chromium carbene complex. So, this is a very elegant route whereby the NHC precursor is converted to transition metal NHC complexes. Now, as mentioned in our earlier discussion, Ardengho was succeeded in preparing free NHCs, and he did that by putting steric bulk on the nitrogen substituent, which would prevent the carbene, free carbene to dimerize, and this was successfully done by putting adamantyl as the N substituents, which led to isolation of free carbene. So, Ardingo's isolable carbene was obtained when bis adamantyl substituted imidazolium halide was treated with sodium hydride as a base in THF and DMSO as a catalyst to give the free carbene plus hydrogen plus NaCl. This free carbene was obtained in high yield, about 96% yield, and was characterized with all techniques including X-ray, and had a melting point of 240 degrees centigrade, which showed how stable this carbene was. So, this was an important breakthrough in being able to isolate transient species, which otherwise are extremely difficult to isolate and had only been observed in by some very sophisticated spectroscopic techniques. Ardingo succeeded in this endeavor by adopting two approaches. First, by putting bulky groups like adamantyl groups around the carbene moiety, which prevented this free carbene in reacting with another moiety to give a olefin complex. So, this steric bulk was an important milestone in isolating free carbene. The other, apart from the steric, the electronic strategy which Ardingo put in place for isolating the carbene was to have a heteroatom flanking the carbenic carbene. So, there are two heteroatom flanking the carbonic carbon, and that would stabilize the carbonic center by the electron with by its minus I effect, would stabilize carbonic lone pair by minus I effect, and hence decrease its reactivity. With the successful implementation of this strategy, which had both steric as well as electronic components towards isolating this free carbene, a lot of catalytic reaction using transition metal carbene complexes came into being, and their role as catalyst in this transformation were looked at very seriously. These NHCs, as mentioned, was found to not only make bonds to transition metals, they formed bonds to various electron deficient entities like protons or electron poor species, as well as electrophiles. So, various carbene adducts that have been reported with free carbene are shown below. For example, the proton adapt with two acetyl substituents Similarly, a I plus stabilized by 2 carbene mesetyl magnesium diethyl mesetyl aluminum H3 it even stabilizes various metal in their low valent oxidation state like bis N-heterocyclic carbene, which has a 0 or plus 1 oxidation state, and that is true for M equals nickel, platinum, then copper, silver, gold. So, what it brings to the fore that carbenes not only can bind to transition metal, but it also can bind to various electrophiles or cationic sources and stabilize them. Furthermore, because of the presence of bulky substituents on the nitrogen atom, the group which is flanked by the carbene is well protected and stabilized, and in this way reactive metals in their low oxidation state have been stabilized using carbene ligands. Now, regarding the classification of carbenes, we had discussed and we have found that there are two classes of carbene, Fischer carbene as well as Schrock carbene. Fischer type and Schrock type. So, even though a carbene is represented by Cr2, the electronic nature of bonding differ. The type of bonding differ between Fischer type as well as Schrock type carbenes. And what has been found that Fischer type carbene is mainly in the singlet state, where carbene where this Cr2 moiety has two orbitals, one in plane which contains the electron and which is full, and the other which is outer plane which is empty. So, this is filled sp2 orbital and this is empty pz orbital. So, we have two orbitals of which one is filled, another is empty, and hence this is called a singlet carbene. Fischer Schrock type carbene are however different. They are generally called triplet carbene, and electronically, though the carbonic center is still sp2, but both the orbitals has one electron each. So, this is C sp2 similar to what it is, but this is half filled as well as the Pz is also half filled. So, this type of carbene represents triplet carbene. So, as the orbital of this carbene are different, their and the electronic structure of these carbenes are different, their engagement with the metal center is also different, and they define different kinds of reactivity. So, let us now look in details about the type of reactions which are present or type of interactions which are present in Fischer and Schrock type carbene complexes. In Fischer type carbene, there are two types of interactions. One is metal to ligand sigma donation, and that is given by R. This is a sp2 orbital and this is full containing 2 electrons, and this is a empty dz orbital empty orbital. So, this is a donation from full to empty, and this is appropriately said designated by metal ligand sigma interacting orbital. The next type of interaction is the metal to ligand pi back donation, pi type interaction, where a metal full orbital this is metal d pi type orbital donates its electron to the empty Pz type orbital. So, in this case this one is full and this is empty Pz orbital, and then the donation is happening from filled to empty. This is from filled to empty, and this is from filled to empty. So, this is metal to ligand pi interaction. Now, despite the fact that both of these interactions are happening, both are of sigma type, in the sense that dative interaction of the sigma type happening in the forward direction, and similarly a dative from filled to empty pi type interaction is happening on the reverse direction, and this is the interaction which is prevalent in Fischer type of carbene complexes, those represents singlet carbenes. So, with this I summarize the topic that have been covered in today's lecture, which involved various synthetic protocols that are available for preparing the Fischer and Schrock type carbene complexes. We have also looked at the stability of these two type of complexes, looked at the electronic nature of these two type of complexes, particularly the Fischer type ones being the singlet type carbene, which are highly reactive as compared to the Schrock type ones, which are of triplet type. In the Fischer type one, there is a filled sp2 orbital and empty pz orbital which participate in interaction with the metal center. As for the Schrock type ones, both the sp2 carbene orbital as well as the pz orbital both contain one electron each, and each of them is half filled, and this is how they are in the triplet state, and that they interact with transition metal with these two type of orbitals. We have looked into the various protocols which are responsible for that, and with that let me conclude today's lecture, and we will take up the carbene in bit more detail in looking into various properties and reactivities of metal carbene complexes, the ramification of these two type of interactions in terms of the properties that they exhibit. We have in the following class. In this particular class, we have also looked at these very famous N-heterocyclic carbenes, their stability, how they are stabilized to get a free carbene where dimerization or the olefin formation has been suppressed, and this was first done by Ardego, and the strategy which was successfully used was not only to put on bulky sterics to prevent dimerization around the carbonic center, but also to put electron withdrawing heteroatom that would stabilize the free carbonic lone pair and prevent them from reacting. So, with this thank you for being with me in this lecture, and I look forward to being with you in the next lecture, where we will take up few more reactivity of metal carbene complexes. Till then, goodbye and thank you.